Logarithmic functions. Do you know what they are? Since you clicked on this video, I assume that you'd want to know what it is. Hello viewers, I am Camille Castro-Opriano, here with my other groupmates, and we present to you our topic about logarithmic functions. Before we begin the presentation, we'd like to go over the objectives that are expected to be achieved at the end of this video. Here we have the following. Number 1. Correctly write equations in exponential form to the logarithmic form and vice versa. Number 2. Familiarize the different laws of logarithmic function. Number 3. Learn how to change simple to expanded logarithmic functions and vice versa by applying its laws. Number 4. Learn how to evaluate logarithmic functions. Number 5. Learn how to find the value of x. And lastly, number 6. Learn the significance of logarithmic functions in life problems. With that enumerated, let's proceed to the presentation. So what are logarithmic functions? These are defined as an inverse of exponential functions. Both logarithmic and exponential functions are related as they can be both expressed interchangeably. These functions are denoted with the letters L, O, and G, or log, which is the abbreviated word for logarithmic. When log is used without any subscripted number, it generally refers to the common logarithm base 10. What is it for, you may ask? It is used for dealing with large numbers while manipulating numbers in a more manageable size. Of course, dealing with big numbers is time-consuming and no one would want to be dealing with them, which is why mathematicians such as John Napier, the inventor of logarithmic functions, thought of this idea to help future mathematicians with their complex calculations and made mathematical computations more manageable. An exponential function is defined by the equation y is equal to a to the power of x. On the other hand, the logarithmic function is defined by the equation x is equal to log base a of y, wherein a is greater than 0 and not equal to 1. Let's now move on to expressing exponential functions to logarithmic functions. First example, a to the power of 0 is equal to 1. In logarithmic function, it is expressed as 0 equals log base a of 1. Second example, 2 to the power of 4 is equal to 16. This function is expressed as an exponential function, but in logarithmic function form, it becomes 4 is equal to log base 2 of 16. Third example, 3 to the power of negative 2 is equal to 1/2. It becomes negative 2 equals log base 3 of 1/2. Fourth example, 7 to the power of m is equal to 49. It will be expressed as m equals log base 7 of 49. Last example, we have 5 to the 5th power is equal to 625. In logarithmic function, it becomes 5 equals log base 5 of 625. From the given examples, did you notice a pattern? There is in fact a pattern. For those wondering what the pattern is, observe how the exponential and logarithmic functions were formulated. The pattern is the exponent of a in the exponential function will become the answer. A remains as the base, and y becomes the argument. In this part of the video, we will be moving on to expressing exponential functions as logarithmic functions and vice versa.
Hello everyone, my name is Ashanti Villaverde and I am here to present to you the next part of this video, which is expressing exponential as logarithmic functions and vice versa. The patterns presented earlier serves as a guide on how to easily convert exponential to logarithmic functions. Let's have a short quiz before we proceed to its inverse. We will be giving you 5 examples of exponential functions, and you will be given time to express them as logarithmic functions. The patterns will be presented here on screen, and feel free to pause the video if you need more time. Now, let's have the examples. The answers for the given are the following. Number 1 is 5 is equal to log base 5 of 625. Number 2, negative 2 equals log base 7 of 1 over 49. Number 3, negative 4 equals log of 1 over 10,000. Number 4, 2 equals log base 12 of 144. Number 5, 6 equals log of 1 million. You may be wondering, where did 10 go in example 3 and 5? Shouldn't it be the base of log? Remember that a logarithmic function is considered a common logarithm if its base is 10, or when no subscripts are seen beside log. Therefore, there is no need to write 10 as its subscript as it is a common logarithm. Now, here we have the patterns for expressing logarithmic functions as exponential functions. Y is equal to a to the power of x, where y is the answer. A is the base of the exponent, which is x. For further understanding, here are the same example from previously. When following the patterns of changing logarithmic to exponential functions, these will be expressed as number 1, a to the power of x is equal to y. Number 2, 2 to the power of 4 is equal to 16. Number 3, 3 to the power of negative 2 is equal to 1/2. Number 4, 5 to the 5th power is equal to 625. Number 5, x to the power of 2x minus 2 equals y.
Hello, I am Josh Lupisan, and in this section of the video, I will be presenting to you the 8 properties or laws of logarithms. These have to be learned in order to be able to evaluate and find the value of x, which will be taught later in the video. First property, the logarithm of 1 to any base is equal to 0. It is read as the log base a of 1 equals 0. To demonstrate, here are some examples. Log base 15 of 1 equals 0. Log of 1 equals 0. Log base pi of 1 equals 0. Log base x of 1 equals 0. Log base 10,000 of 1 equals 0. If you were to convert this into exponential functions, 15 has the exponent of 0, meaning that with every number with an exponent of 0 is always equal to 1. Same goes with the second example, a common logarithm. Second property, the logarithm of a to the base of a is equal to 1, which is read as log base a of a is equal to 1. For example, log base 15 of 15 is equal to 1. If converted into exponential, it becomes 15 to the power of 1 equals 15. For the second example, it is implied to have a base of 10 since it is a common logarithm. The logarithm and its base have the same number, therefore it equals to 1. Third property, the logarithm of a to the power of x to base a is equal to x. Logarithm base a of a to the power of x is equal to x. In simpler terms, when the logarithm is taken of a power raised to the same base, it results in the exponent itself. An example of this is log of 100 is equal to 2. Remember that if there is no subscript of log, the base is 10, and since 100 is a perfect square, change it into exponential form, which becomes log base 10 of 10 squared. Fourth property, the logarithm of a to the base of a to the power of x is equal to 1 over x. It is also read as log base a to the power of x of a is equal to 1 over x. In simpler terms, when the logarithm is taken of a raised to the power of x with the same base, it results in 1 over x. One example presented is log base 5 square root of 5 is equal to 1/2. Fifth property. The logarithm of the product of m and n to the base of a is equal to its sum to base a. This can be read as the log base a of m and n is equal to the sum of log base a of m and log base a of n. An example of this property is log base 4 of y quantity x plus 2 is equal to log base 4 of y plus log base 4 of quantity x plus 2. Sixth property. The logarithm of the quotient of m over n to the base a is equal to its difference. It is related to the fifth property but is separated by the minus sign instead of the plus sign. Seventh property. The logarithm of a power. This property is denoted as log base a of m to the power of n is equal to n log base a of m. Just like example 1 here, log base 2 of 4 to the power of 16, this is an example of this property since the argument has an exponent. And the eighth property, the logarithm of a root. Whatever is the value of the index in a root, it will be moved to the denominator. This is read as log base a of the nth root of m is equal to log base a m over n. Log base 2 of the sixth root of 36 is equal to the log base 2 of 36 over 6 is an example of this property. Before we proceed to expanding and simplifying logarithmic functions, here is our technique for properties 1 to 4. If you get confused between those properties, this is for you. The first a's represent the base of the logarithm, while the rest represent the argument. For a, x, a, the x refers to the exponent of base of a. To understand it better, let's try to go over the previous examples and check if the technique can be applied. Let's focus on this example first. Log base 15 of 1 equals 0. 15 is the subscript beside log, therefore it is our a, and 1 on the other hand is the argument. If you are able to apply the first technique, which follows a1 equals 0, the logarithm does indeed equal to 0, making the technique valid. Log of 10 equals to 1. This follows the AA equals 1 technique. Log base 4 of 4 to the power of 3 equals 3. Follows the AAX equals X technique. Log base 6 to the power of 3 of 6 equals 1/3. Follows the AXA technique. As you can see, using the technique serves a guide when it comes to applying these principles in expanding, simplifying, and evaluating logarithmic functions.
Welcome to the part of this video where we test your knowledge and application skills in expanding and simplifying logarithmic functions. The only way to do this is to be familiar with the principles of logarithms. Without further ado, let's proceed to expanding logarithmic functions. Example 1. Log base 7 of ab squared over c cubed. It may seem complicated at first glance, but all you need to do is to take things step by step. Focus on each number and variable and separate them all with operations. In this example, we need to apply the logarithmic principle of product and quotient. Since it is divided by a fraction bar and since there are two variables in the numerator. When expanding, focus on the numerator first. A and b squared are both in the numerator, so it becomes log base 7 of a plus log base 7 of b squared. Now for the denominator, which is c cubed, it becomes log base 7 of c cubed. And now the answer will be log base 7 of a plus log base 7 of b squared minus log base 7 of c cubed. Why is the operation after b squared negative? It is because c cubed is located in the denominator, and by applying the logarithmic principle of quotient, anything below will be separated with a negative sign. Don't forget to apply the property of a power, where you will place all exponents before log. And so, the final answer is log base 7 of A plus 2 log base 7 of B minus 3 log base 7 of C. Example 2. Log base 2 of the square root of A cubed and B cubed over the square root of x, y, and z. Again, focus on the numerator first. Since the logarithm has a root, apply the root property, which will equal to log base 2 of A cubed over 2. A has an exponent, so it has to be moved before log. So now it will become 3 log base 2 of A over 2. Do the same thing for variable B. So now it will become 3 log base 2 of B over 2. Separate both of them with a plus sign, since both of them are in the numerator. Now, we will go to the denominator. Separate them with a negative sign, since they are in the denominator. And so, the final answer is 3 log base 2 of A over 2 plus 3 log base 2 of B over 2 minus log base 2 of x over 2 minus log base 2 of y over 2 minus log base 2 of z over 2. Example 3. Log of AB over CD. When expanding, it becomes log of A plus log of B minus log of C minus log of D. We are going to let you answer the last 2 examples to check if you learned how to expand logarithmic functions. Feel free to pause the video if you need more time. Here are the answers for examples 4 and 5. For example 4, the answer is log of 10 plus log of 100. And for example 5, the answer is log base 14 of 5 plus 2 log base 14 of A plus 5 log base 14 of D minus log base 14 of 4 minus log base 14 of x over 3 minus log base 14 of y over 3. Simplifying logarithmic functions is just the opposite of expanding. If it is positive, it is in the numerator, and denominator if it is negative. If it is expressed as a fraction, then it involves a root. When simplifying logarithmic functions, write the logarithm and its base before simplifying the rest. Let's have example 1. Log of 5 plus log of A minus log of D minus log of C. Both 5 and A are positive, therefore they are located in the numerator, while log of B and C are negative. The simplified answer is log of 5A over BC. Example 2. Log base 2 of C over 2 minus log base 2 of A over 3 plus log base 2 of D over 2 minus 5 log base 2 of B over 3. All of them are expressed as fractions, so that means they all have roots. Next, identify which of them are positive or negative. Apply the property of roots, and so the final answer is log base 2 of the square root of C and D over the cube root of A and B to the power of 5. Example 3. Log base 2 of A minus 3 log base 2 of x minus 2 log base 2 of y over 3 plus 4 log base 2 of b over 2. Again, the first thing you need to do is observe which are positive or negative. Those that are positive will be in the numerator, while the negative ones are in the denominator. So, now we have log base 2 of a square root of b to the power of 4 over x cubed multiplied by the cube root of y squared. That still isn't the final answer yet, since you can still simplify the square root of b to the power of 4, which will become b squared. Now, our final answer will be log base 2 of a b squared over x cubed multiplied by the cube root of y squared. Once again, we'll be presenting to you examples 4 and 5, and you will now be the one to simplify the logarithmic functions. Here are examples 4 and 5. For example 4, the answer is log base 3 of x cubed over 27. Example 5. The simplified version of both equations are log base 5 of 3 squared times 25 through the logarithmic property of a product. Though 3 squared can still be simplified, therefore it becomes log base 5 of 9 times 25. Multiplying both of those together, the final answer will be log base 5 of 225. Now that you've learned how to expand and simplify logarithmic functions, it appears that you are now ready to proceed to evaluating logarithmic functions and finding the value of x.
Evaluating logarithmic functions is when you solve for the numerical value of the equation by applying its properties. Ensure that you are already familiar with those properties to be able to evaluate logarithmic functions. Let's now proceed to the examples. Example 1. Log base 2 of 4 plus log base 2 of 2. When evaluating logarithmic functions, apply the appropriate logarithmic principle for evaluation. Focusing on log base 2 of 4, it doesn't have an exponent, although it has a perfect square, which is 4. Next, change 4 into 2 squared so that now it will become log base 2 of 2 squared. Applying the AAX technique, the evaluated answer for that is 2. And now for log base 2 of 2, if there is no exponent present beside the number, and if the number is not a perfect square, the exponent is equal to 1. Applying the AAX technique again, the answer will be 1. And so, adding the evaluated answer of log base 2 of 4 and log base 2 of 2, which is 2 and 1, the final answer will be 3. Example 2. Log base 5 of 125 plus 2 log base 5 of 5. For log base 5 of 125, 125 can be expressed as 5 cubed so that it will have an exponent, and now it will become log base 5 of 5 cubed. With that, we can apply the AAX technique, which will have then 3 as its answer because it is the exponent. Let's proceed to 2 log base 5 of 5. It follows the logarithmic principle of a power. So, if it were to be changed, it becomes log base 5 of 5 squared. And again, applying the AAX technique is the most appropriate technique to be used for this example. And so, the answer for that will be 2. Adding 3 and 2 sums up to 5, which is our final answer for this example. Example 3. Log base 3 of 3 minus log base 3 of 27 plus log base 3 of 1. In this example, the AAX equal x and A1 equals 0 technique is applied for evaluating these functions. So if it are all to be evaluated using those techniques, the answers will be 1 because the exponent of 3 is 1. 3 because when changing 27 into exponential, it becomes 3 cubed. And lastly, 0 since it applies the A1 equals 0 technique. Now, it's your turn to solve and evaluate examples 4 and 5. As the drill goes, feel free to pause the video if you need more time to solve. Example 4, which is read as log of 10 to the power of 4 minus log of 100 minus log of 10, can be evaluated with AAX technique, which gives us 4, negative 2, and negative 1. Don't forget that 100 is 10 squared, which gives us the answer of 2. But since there is a negative sign, it becomes negative 2. Adding those together, we have 1 as our answer. And example 5, read as log base 2 of 1 plus 2 log base 5 of 25 over 3 minus log base 64 of 2 can be evaluated by applying the a1 equals 0, aax equals x, and axa equals 1 over x techniques. Let's go over them one at a time. Log base 2 of 1. We will apply the a1 equals 0 technique because if it were to be expressed as exponential function, 2 will have an exponent of 0, and if that happens, any number raised to the power of 0 will equal to 1. 2 log base 5 of 25 over 3. Copy the 2 and 3, then focus on the log base 5 of 25. We will only simplify it if we are finding the value of x, which will be discussed later in this video. And so, log base 5 of 25 becomes log base 5 of 5 squared. Applying the AAX technique, the answer will be 2. But don't forget the fraction as well. It will become 2 times 2 over 3, which makes it 4/3. And now for log base 64 of 2, we'll be applying the AXA equals 1 over x technique, which will give us 1 over 6, but it is negative due to the operation before it. If 64 was expressed as the base with an exponent, it becomes 2 to the power of 6. It will now become log base 2 to the power of 6 of 2. Adding 0, 4/3, and negative 1 over 6, our final answer will be 7 over 6. When finding the value of x, you need to observe this pattern, expanded to single to exponential. It means that you have to check if the given equation is expanded. If it is, then simplify it and express it as an exponential. If the given equation is simplified, however, you can immediately change it to exponential function, and then further solve the problem until you get the value of x. Example 1. Log base 2 of 8 over x equals 3. First, identify if the equation is expanded or single. In this example, the given is already single. That means we can proceed to expressing it as an exponential function. Remember the pattern in changing logarithmic to exponential function. This will now become 2 to the power of 3 equals 8 over x. And now, we simplify to find the value of x. First, by simplifying the value of 2 cubed, which is 8. Second, transfer x to the other side of the equation to get rid of the fraction, which now makes it 8x equals 8. Divide both sides of the equation by 8 to remove any number beside x. And now, we have 1 as our final answer. Example 2. 2 log base 3 of x plus log base 3 of 9 equals 5. Again, identify if the given is expanded or single before anything else. In this example, it is in expanded form, so we need to simplify it before moving to expressing it as an exponential function. 2 log base 3 of x will become log base 3 of x squared. Now, since both logarithmic functions both have the same base and are positive, that means we can apply the logarithmic principle of a product, making it log base 3 of 9x squared equals 5. Next, we express it as an exponential function. 3 to the power of 5 equals 9x squared. Simplify 3 to the power of 5, which is 243. Divide both sides by 9 to remove any numerical coefficient beside x, which results to 27 equals x squared. Divide both sides with square root to remove the exponent of x, making it the square root of 27 equals x. That is still not the final answer, as the square root of 27 can still be simplified into 3 times the square root of 3, which is the final answer for the example. Example 3. Log base 2 of 8x equals 6. It is already simplified, so we can proceed to expressing it as an exponential function immediately, which is 2 to the power of 6 equals 8x. Simplify 2 to the power of 6, resulting to 64. Divide both sides with 8, leaving us with 8 as our final answer. I'm sure you know what's next. That's right. It's your turn to find the value of x for these last two examples of this video. And one last time, you are free to pause the video if you need more time for solving. Here are the examples. So here are the answers. Example 4. Log of 2x plus log of 5 equals 3. It is an expanded form, so now it becomes log of 10x by applying the principle of a product. Change it to exponential function, 10 cubed equals 10x. And then simplify by changing 10 cubed to 1000. Divide both sides by 10, leaving us with 100 as our value of x. And lastly, for example 5, log base 3 of 27 over x equals 2. It can be expressed as exponential function since it is already in a single form. 3 squared equals 27 over x. Simplify 3 squared and transfer x to the other side of the equation to remove the fraction. Then divide both sides by 9. 3 is the value of x for this example.
After all this learning and solving, you may be wondering, why are logarithmic functions important? It's not like we apply this on our lives every day. That is correct. But this topic provides several purposes in different fields or aspects, such as number 1, geology, specifically in measuring earth waves. Number 2, chemistry, when it comes to measuring acidity levels. Number 3, in finance and interest rates, as its formula involves the application of logarithmic functions. Number 4, population growth and decay, also known as the increase and decrease of population. And lastly, number 5, radioactive carbon dating. Every lesson in math has their significance in today's society. Without math, things will be completely different from here on out. Yes, the lesson progressively got more difficult, but it is still important to learn about it, which is why we shouldn't take math for granted. And that's the end of our tutorial. Thank you for watching.